All right. So anyway, but yeah, section 10 basically is kind of like, I like to think of it like the big start of really machine learning and predictive modeling, linear regression. Linear regression has been used like for so long, but it really comes from the fact from like section 9, we start off with the z-score, the z-test, basically saying, well, okay, how do we quantify if these, for example, if you're comparing two samples, saying, do these samples belong to with each other, or does this sample belong with the population? So that's kind of like where I think the linear regression kind of starts coming out from, and basically building up relationships of like essentially different variables. Oh, man, my chair is all weird. Okay. So first of all, let me just ask you guys, because I'm sure some of you guys at least have heard it. Who's at least heard of linear regression? Okay. Good. So kind of going around is, let's see here. If you had to put like, when is the last time you probably heard linear regression or used it? Would you say like high school, maybe university, actually a job level? What would you say, Assad?
Actually, I think we had to do a linear regression model for the intro course for the program.
Oh, good. I didn't realize that. Okay, cool. So you guys have seen linear regression. Awesome. Okay. Well, that would make things a lot quicker. So let me go ahead and share my screen. Hey, Matt. Glad for you to join us.
Hi. Sorry, I'm late.
No problem. It happens. Okay. So everyone can see my screen right here going on. Yeah, cool. All right. So
is this screen something you're going to share in the future?
Yeah, I do need to share section 9s, which I haven't. Right? Yeah, I had some issues with it. One of the reasons why the images I put on there weren't linked properly, so I have to kind of fix those and then make sure to share it out. I'll make sure to I'll try to get it out to you guys at least yesterday's sheet today, and I'll try to make sure to get this one out today. I think I can get this one out quicker. So
all right,
look for that. It might be a little late on your guys' time, but hopefully by this evening. But yeah, I'll make sure to share it. Cool. All right. Okay. And let's see here. List of, so it's Paul asking, could we get a list of the links that Eli mentioned as well? I don't think I ever sent that out. Oh yeah, was that for
I think section 8 stuff he never sent.
Yeah, okay, I'll remind him. Yeah, I'll make sure.
No, everything if possible. We were talking about and I'll make it if he doesn't want to, but just having like a doc where we can look at everything since Slack messages disappear.
Yeah.
Like a shared Google Doc or something.
Yeah, we can see. I think there might be something like that right now. I'll have to check. I know there's one that has a bunch of resources, which includes other instructors of what, recordings of them. I don't know if you guys know what I'm talking about or have seen that sheet. Okay. But I don't think that includes necessarily some of the stuff he's shared. So we'll either add it onto that sheet, or we'll make sure to have one cohesive sheet that you guys can see the stuff that we added on. Okay. Let me make a little note of that. But yeah. Okay, so, but going back to today's thing, and I'll share this out eventually, the main kind of concept, I think, of a linear regression in the curriculum that you go through section 10 is basically you're trying to find relationships. You're trying to see how do variables match together. And we actually start off with a simple linear regression, which really just looking at like basically two different variables, So when I talk about two different variables, you'll also hear them called as features. So has anyone heard that term before, like seeing features in the data set? So this will become more and more common, especially if you do machine learning. Features are basically just like different aspects of the data. So for example, if you were measuring, let's say, baseball, like how, I don't know, say baseball or whatever, and a feature might be saying, how many RBIs a team has, how many, home runs do they have? It could even be like, what is the cost of a ticket? Like those would be different features of your data set. And those are usually synonymous with variables. So the first thing we can go into is something called covariance. And so covariance, as you might kind of guess, plays off of variance, right? And variance related to standard deviation. And can someone remind us what standard deviation or variance, what is it explaining? Like what does it summarize? Any volunteers?
Just the distribution of your data.
Good, right? Distribution, usually here as the spread, okay? And so really covariance comes from variance, and it's the measure of dispersion or distribution or spread, however you want to phrase it, specifically from the mean. And so standard deviation variance basically comes a lot from, what's it called? Basically, it's built around usually the normal distribution. It doesn't necessarily have to be from the normal distribution, but that's when it makes the most sense, because we saw the normal distribution, we had that nice, beautiful curve, and we can see exactly the 68, 95, 99 rule, right? So let's see if I draw it. So that's our variance right here. And you can see, you guys probably have seen this notation before with the sigma, with the summing and stuff like that. Basically, it just means we're adding them all up together, taking each data point and comparing it to the mean, and then standardizing that. One thing to kind of note, just because it does come up a little bit, is that this right here, this divide by n, sometimes you actually see as n-1 in some equations. And the reason why is because this is supposed to represent for the population. And it turns out there's a subtle reason why, if you look at just a sample, which is a portion of the population, you actually do n-1. The curriculum does actually point to a good article for that, so I won't go into details, but there's actually a mathematical proof of saying why you do n-1 versus n. Same thing will happen when we look at covariance. So just know that this little n right here will be n-1 for population, okay? But covariance basically is measuring two different variables from each other. So you can kind of see if you look at the math closely, you can see it's actually really similar. We have the n down here. We even use a lot of times the same symbol, sigma, xy, to represent our covariance. And it's between the variables x and y, so those two features. So we take basically from each point in x, each point in y, and we compare it to the population mean of either x or y. Can you guys see that okay? It's not too small, right? Thumbs up if it's looking good. Okay, cool. So this is the calculation here. And one thing I want to kind of note is that you'll see a few formula in here, and don't feel like you have to memorize these formula. I think it's important to know where they're coming from and maybe how they're structured, and what variables involve. But in reality is that when you're doing a lot of this data science stuff, you are actually using a package or a library to figure out this stuff. You very rarely do it by hand. And if you do it by hand, to be honest, you go look it up and make sure you don't have it wrong. Because obviously, for example, if you forgot this squared part, that would be a huge issue. You would have a different kind of calculation. Okay, so kind of going into what it really means, we kind of touched a little bit on that. Oops, I clicked there. There it goes. The covariance, as we kind of noticed, is that just like the standard deviation, or I shouldn't say standard deviation, but the variance, it can basically go from negative infinity to infinity, right? It can be very, very large, which actually gives us an issue when we're trying to look at saying, well, we want to compare, say, well, what's a stronger relationship? Is X and Y a strong relationship, or is Y and Z a stronger relationship? And if you have something that's, for example, like 5.2 versus 6.3, it's not really quite clear. It's like, well, which one's really that much stronger? And it just becomes hard to do it. So we need a more standardized way of looking at it, and that will lead us into correlation. But one thing to kind of note is that, because, to be honest, most time we won't talk too much about covariance. We'll usually talk about correlation, but that's really where correlation will come from, would be from the covariance. And we'll see this in correlation, where a positive covariance basically means that they are positively correlated together. And so when we say positively correlated together, if I have, oops, there we go. If I have, oh gosh, I can't draw today. There we go. If I have a graph where we have X and Y, when we have a positive correlation, basically it means that as we increase in the X direction, the Y also increases. It might be a little increase, like for example, maybe it's like this, but that's a positive correlation. A negative correlation is basically, it's still correlated, they just correlate in an opposite direction. So for example, as X increases, maybe Y decreases, okay? And of course, this doesn't have to be a straight line, it can be a curve and all that stuff. And usually you won't see lines in your data like this. Instead, what you'll see a representation is actually data points, and basically trying to figure out if these points generally move up as X increases, or move down. Anyone got to guess what a covariance of 0 might tell us about the data and how it's correlated?
there's
Yeah,
no
that
correlation
it's.
between the data.
Oh,
No, that's good. Go ahead. Assad, go ahead and finish.
That that was my guess. No correlation between the data.
That's right. Basically, there's not really much things correlated together. Basically, sometimes when X increases, sometimes Y increases, sometimes Y decreases, and it doesn't seem to add up in a very particular pattern, okay? And that basically means like, okay, maybe they're just not related at all, okay? So if we go into correlation now, which is what covariance leads into, again, our little motivation here, is that this is our calculation. Now, one thing you should note is that, and this goes for almost all statistics, or every statistic that we measure, is that this is a way to summarize the data. And in a lot of ways, the data are the most complete representation that we have of that world, of that that kind of like world that we're looking at. And so when we actually do a statistic, when we do a model, if we're doing anything, we're basically trying to summarize this world that we're looking at, which is our data. And if, as we kind of like take, I'm trying to kind of talk a little more as a bigger philosophy. So understand like your statistic number doesn't actually necessarily mean anything unless you understand what it's representing, because you're basically taking away a little information. Like if you just summarize everything, for example, if you take the mean, that tells you one instance, but doesn't tell you everything about it. So you need multiple points to help summarize things. So know that there are different ways to calculate these different statistics. So for example, here we have Pearson's correlation R, which is calculated this way. And I actually kind of wrote this out. Again, you don't have to memorize this at all. I would strongly suggest not memorizing this. I think your brain power could be used for a lot of different other things. But I kind of want to relate how this guy right here will look very similar to the covariance. In fact, you can actually define the correlation based around the covariance of this guy. And you can see right here, for example, this looks very similar to the, what's it called? The state variance, not the covariance, but the variance. So basically that correlation kind of combines those things. It basically scales down, it normalizes the covariance down to -1 and 1. And then also allows us independent units. So we don't have to worry about saying, well, we're talking about feet, we're talking about, you know, like the correlations like in feet, meters, or whatever you're talking about. You can just say, oh, the correlation is, you know, or so say R, the R is basically 0.8, and that would tell you a number. You don't have to worry about the units directly, okay? So you guys probably have seen this before, just because I feel like statistics is such a huge part of every field, is that we see a different correlation factor. So we can see one is at this far left here, and to the right to -1. And it's actually in the curriculum too. So you can actually see these points right here. These points on the far left are positively correlated, and they're correlated very strongly, meaning that pretty much every time X goes up, Y goes up the same amount every single time. And then this right here, we see something that's not quite 1, but there's still that like kind of general movement. And we kind of move further off to the right to 0 correlation that Assad had mentioned. There's no correlation in there. That's what the 0 represents. But you can kind of see in between those parts, you can see some pattern in there, but it's not 100%. And most data, you probably won't see it right away, just because there's so many data points, and it'll be something to kind of be aware of. But again, a lot of times when we do these kind of values, like for example, correlation, covariance, it's great. You can make a computer compute it, but honestly, one of the best ways for you to double check things very quickly is just to plot it out and see what does the data look like. And you can very quickly kind of tell, and we'll talk about a little bit when we're looking at linear regression, when it works and when it doesn't work, or when it's really useful, that it matters on just looking at the graph itself. So first of all, so that's covariance and correlation. Any questions on these? These hopefully don't feel too complicated at all. Thumbs up if you're feeling pretty good about this so far. Yeah. Okay, cool. I think Matt might be frozen over there. I can't tell. All right, so that's, okay, no problem. So we got covariance, correlation, and then this really leads us into statistical learning. And statistical learning really is about kind of like the motivation of why we ended up doing more, like when we talk about machine learning, that's kind of like closer to doing this learning part. And basically we're using statistic to do a better and better job into predicting our data. And that's really what statistics are. So when we talk about a model, for example, a statistical model. What we really mean is something that takes this data, like for example, you can see I have all of this data right here, okay? And I want to summarize it. That's the whole point of our statistics. That's the whole point of a model, is saying it's not necessarily the most correct thing, right? It just means that it helps explain the data. And so the curriculum calls it a function, but I actually like calling it a mapping, which is more of a mathy kind of term, but it really doesn't have to be like a nice, beautiful line. It doesn't have to be a nice, beautiful, parabola. You'll see those different kind of things. Like for example, like maybe a statistical model could be this, like if I just travel along this line, that's where the points would end up. Or it could even be like a really crazy model could literally be connecting these points together, right? Now, there's a whole reason why maybe you don't want to use that kind of model, but it is a model, right? It does, this one actually, if you look at the really curvy one, makes a lot more sense for the data. It looks like, it's like, oh, that would fit perfectly, right? Every time you put in a point that's on from your actual data and you put it into your model, it perfectly describes the result. And you're like, cool, that's a great model. But there's actually a lot of reasons why that might not be a good thing. And this is kind of leading into a little more about like something called overfitting and why we do something called validation, but we'll get into that in a second. But this right here is an example. This blue line would be a model, and that's actually a regression line. And basically, you'll actually notice if you look carefully, this line barely touches any of those points, but the idea is that it gets a general idea of what those points are doing. So if you have a feature point, maybe the feature point's over here, you would have it pretty close. Maybe your feature point might actually end up being way off over here. In that case, if you get a lot of new data and you find out that your model's not adding up to it, then you need to adjust it, okay? So that's the basics of when we talk about a statistical model. And of course, I kind of will quickly talk about this. There are really three flavors of variables. There's your independent variable, your dependent variable, and then usually there's something that we don't really talk about too much, but it is there, is your controlled variables. And so independent variables are, the best way to describe this, like back when I was teaching like 8th grade, is your independent variables are just things that you can either adjust or that will cause the effect. Okay, so you might not actually be able to adjust it in an actual experiment, but the fact that you can see that change. So usually independent variable, for example, time, like what time of the day it is, usually tends to be an independent variable. Something that can change, basically you have no control over it and it affects everything else. And of course your effects are dependent. Controlled are things, basically other variables that hopefully are not affecting the rest of your relationship between an independent and dependent. Okay, and then again, independent variable goes on your x-axis, dependent variable goes on your y. At least that's the convention. Hopefully that's all pretty standard and you guys don't feel like I need to go into that. Okay. Some terms that we're going to talk about are parameters. So we kind of talked about parameters with a Gaussian and for a normal curve. Parameters just basically saying, okay, we have this model and then we say we are going to fit the model on, let's say linear regression. And you basically take in parameters and that's how you make a new model. So all the models will basically just change just by parameters. Everything else is the same. And we're kind of interested in seeing this kind of terminology, which we use a lot in predictive modeling, like machine learning, for example. We'll call them features and targets. And basically features are the independent variables. Target is basically your outcome, your effect. So you might actually, for this thing in the first section 10, we only look at like really one feature and one target. But later on, you might actually have multiple features to explain one target, okay? And you can probably think of all the different situations that would actually arise from, right? So this is where we kind of talk about statistical models, but this is where actually statistical learning comes in, and that is something called model validation. This is actually what causes, quote unquote, the learning part of it. Basically, you're taking one thing, you're trying something out, and then if it doesn't work out the right way, we'll talk about what that means, you adjust that model. So that's where we get into something called validation. And validation is actually a really interesting topic about like how you do validation. We'll talk this a lot more as we get deeper and deeper into how we do modeling, including like machine learning. But basically the idea is that you have the total data set and split it into a training set and a testing set. And the idea is we create the model from the training data set, like this portion of the data that's used just for training. And then we take some of the data to basically evaluate the model, see how well it's doing, and evaluate saying, was this a good model for our data? So I kind of wrote this little question: why would we want to do this? What might be the motivation to actually take our data and split it into a training part and a testing part? Anyone got an idea?
If you don't have any other testing data, then you have no way of knowing if you've overfitted or something like that.
Good. So you're using the terminology there, overfitting. So when I say, like, when Matt said overfitting, can you maybe go in a little more detail of that, Matt? Or if someone else knows what overfitting is, they can explain that.
So, as you mentioned earlier, if you are, if you have data that shows how one thing changes with another thing, and you just assume that the correlation is exactly as you would think from just the data you have, then you're going to get you're getting a rough picture of what the data would really show with a larger amount of data, or what the real correlation actually is.
Yeah, I think you got that right. Is that basically when we're doing that testing part, if we were just to use the full data set, so kind of going converse real quick, is that why would we split up the training and testing data? Because imagine you have all this data and you take out some of it for testing, then you have less data to work with, right? You're hurting yourself, right? But the problem is, like Matt said, is that you could overfit. So for example, if your model, like I kind of drew out, just connected those dots, right? Well, you're using the full data set now to completely describe what your model should do. So the problem is that if you tried saying, okay, how well does this model fit, basically explain my data, you'd say this model is 100% perfect. It's awesome. It's amazing. Like it works for the data. But then the instance you get one little data point, a new data point that's not on that model, it's likely not going to be explained well by that model. It's probably going to be completely off. So the idea is that you actually reserve some of those data points to actually say, okay, I'm going to reserve randomly, say these parts over here, and maybe usually it's like a 20-80 split, depending, what the situation is, but that usually is pretty common. And you say, okay, I'm going to build the model off of just these things, off the ones that were not used for testing, build the model as best I can, and then say, okay, now I'm going to test it out using these training points right here. And so it's kind of like the idea is like if you're studying for a test, you usually wouldn't study everything because that's really, first of all, really difficult, but you'd probably like study a few different groups of things. And then when you test to see if you know your knowledge, you wouldn't give literally the same, if you were a teacher, you wouldn't give the same exact questions on the test as the homework, right? Because then obviously, well, if someone already knows all the questions on the homework because they've been training on it, right? They've been learning on that, then obviously you're not going to really know the true like knowledge of the student. Okay, that's kind of like a reason why we end up doing that, and we'll see it a lot more again in machine learning. Okay, and then that's where this loss function is, and this loss function can be a very general thing. We'll talk about a loss function for linear regression, but basically this loss function is the way we evaluate. It says, all right, how well is the model doing on the testing data? Okay, cool. So any questions on that? Hopefully this feeling pretty good. So our last part really our main meat is our linear regression. So you guys all are familiar with linear regression, which is awesome. And so our linear regression basically is just a statistical model. It's one way to make a model. And really a big part of, linear regression is the fact that it's just a really quick way to make a model. You don't have to do a whole lot of extra computation. Basically, you take the model, you essentially find if you have your X, you have your Y variables, right? Your feature and your target over here. Oops. You have your feature and your target over here. Then you can just take those points, find the average, and find the standard deviation, and say standard deviation, the sample standard deviation, and you basically got your linear regression right there. You don't have to do anything after that. So it's a very quick way to make a thing, which I think part of the reason why should be a data scientist go-to, Little story time. I was just talking to someone who had an interview or had to interview a junior data scientist. And one thing that they said, they asked about linear regression and they couldn't answer about it. They couldn't understand the fundamentals of what linear regression was and how to actually build it and like, you know, all that stuff. And it's really should be your go-to. We're going to find more advanced things with ML, with machine learning. But really, if you can make a model that works really well with linear regression, you don't need to use more advanced topics because it's just a waste of time, essentially. Like maybe you get a little bit better, but not significantly more, okay? So that's kind of like the motivation of why linear regression is really important, even though it's going to be probably one of the simpler models that we're going to look at in this course. So we're going to create our regression line. And so this is probably, at least you guys have seen this before, is that right? Of actually creating a linear regression. All right, thumbs up if you've seen that on the pre-course. Yeah, okay. Hopefully you guys are feeling comfortable with, or not comfortable, but like at least be aware of that. So I'll go through this really quickly. Basically, it's also called line of best fit. Basically, you're trying to fit the data points, or you're trying to fit the data points onto the regression line, okay? And it's always written as essentially, if you remember back in like high school, it'd be like y equals mx plus b. Curriculum kind of fluctuates between y equals mx plus b to ax plus b to, it even does what's more commonly done as you expand the model out. You'll see it like y equals w0 plus x1 w1. And that'll lead more into multiple linear regression. And basically you can see the format's essentially the same, right? Is that essentially there is a constant term, that's what this number is. It's just a single number. And there's another number here that's being multiplied by our feature to get the target. So that's everything that's going on here. The reason why they write this is because it turns out in a lot of, for example, like neural networks and machine learning technique, you essentially have this part, though instead of having single coefficients, you usually have like vectors and matrices. But again, we'll get into that much later. And then we have our slope here, which is basically the correlation, Pearson's correlation, R. And this right here, SY and SX, these are the standard deviations, but it's very important to note that's the standard deviation of the sample. So usually we'll use like sigma and mu as the population parameters versus using like a lowercase s, and usually it'll be like x bar. Usually they'll say like as the average for that sample. So that's where that distinction comes from. But you'll notice it's the standard deviation of SY, standard deviation of Y and over the standard deviation of X. So that's kind of like that rise over run Y divided by X, if you remember back in school when we talked about slope. So this right here is a good picture, and this is in the curriculum itself. I think this was an awesome one. It shows all the different points of like what the linear regression is, and you can see these green data points right here. They label them as XI, XI, YI. And you guys are pretty comfortable with the notation of like when they have a sub, excuse me, I'm blanking on the name now. When you have that number or letter underneath a subscript, there we are. You guys are used to the subscript before? Okay, cool. So sometimes people get a little tripped up on that on the math notation, but I have a feeling that you guys feel pretty good with this. And one thing they'll note on here is you'll see, this is right here is the whole equation, but you notice there's this little y, and they call it y hat, right? With that little y hat right there. That is saying that this is the prediction right here versus y, like yi, okay? That y right there is actually about the data point, and the y prediction, or the y hat, is the prediction itself. It describes, in this case, the linear regression line, okay? So again, a good diagram here that I would say like if you ever had to like go into an interview and they say like explain to me everything about linear regression, if you drew out this would probably get you like 90% of what they want, just because you see how much it's offset from the line, and you see the actual line, and you can see this intercept right here. So one thing to note is that we can actually get the intercept. So like we can get this equation, we can get the slope, but you'll notice if you remember, like, well, what's that B part? What's that W0? How do I get that part? And there's a subtle point that we'll talk about in a second, is that you actually use the mean of X and the mean of Y, and you say that point, let's say the average of X is like right here, and the average of Y is like right here. Those points are always on the regression line. This will always be on that line. So essentially you can think of the regression line as basically being pivoted about the mean of X and Y. And that actually gives you your base of how we figure out if a regression line is any good. So that's actually kind of leads us back to here, is it any good? So first of all, any questions on any of this stuff? Just kind of going through it really quickly. Cool, all right. So this leads us into how we know if a regression line is actually good. And this one shows basically it's, how do I say this? Usually you'll hear it as like a squared errors or sum of squares. And basically what you kind of do is that I actually think the curriculum set, I don't like the way it phrases it at one point. It says it's seeing how far away the points are. And that's kind of true, but not really. Because we'll calculate this thing called R squared, which really determine how well our linear regression line is. In fact, if you basically use a stats package and you put in calculate the linear regression for me, it'll spit out an R squared value. And that R squared value will tell you how good that regression is. But it's not just based on how far away each data point is from the line, like the curriculum kind of says. It's actually a little more subtle. It actually takes the square of how far away those points are. So it actually says, all right, how far is this data point right here from the line? And we call that the residual. Okay, basically like what's the offset of that? And that's our residual. And we square that. So we actually get a squared value here. And that's what this is representing. That we're basically summing up all the different, if this is another data point, you basically get the squared of that residual and you add up all those squares. So you're actually trying to minimize an area is essentially what's going on when they're trying to find what the best R squared value is. But you'll see right here, yi is the data point. Y hat I is basically what the model predicts yi should be. So that's what this point is right here. This is yi, okay? And basically it's saying, oh, this is where it should be right here. And so that's where this value comes in. And we square that and we sum up all those squares and we sum them all up. And we actually divide it by this guy right here, which is a little subtle, like why do we do this? And you'll see it's yi again, which is the data point like we have up here, minus the mean squared. And what's happening actually here is that this right here is this y mean. And we basically say how far away is that data point from the mean. Okay, and of course then we square it. But it actually comes from the fact that if r squared is equal to 0, that is actually our worst model. It means that it doesn't do a good job explaining everything. Okay, and what that comes from is actually that we're using the mean to predict what basically we use the mean to predict, saying, okay, this is the worst possible model. Trying to explain it, just like say, all right, for example, if you said like, what's trying to give a good example of this, but let's say you say, okay, we have a bunch of people who are their height versus their age, right? And you take a bunch of your data and you basically average them all together, and you average all of that and say, okay, the average age is 35 in this population. And so you say, okay, that means that no matter who I get, no matter what their, I'm sorry, I'm messing this up. Let's say their average height is 6 feet. And so their height is 6 feet, and you have a bunch of ages, and you say, okay, I have their age, how tall are they? And you just say, it's 6 feet. Every time someone says, if they're 30 years old, 6 feet. If they're 50 years old, 6 feet. If they're 2 years old, they're 6 feet. That's basically what your worst model is. You just say, it's the same everywhere, it's just the average. So the way this would look like is that if you took a least regression line that had an R squared of 0, which would be like the most awful model essentially, it would just be a straight line right through the mean. which would be the X mean and the Y mean. So that's our worst model. And we're actually comparing, saying, hey, how good is our linear regression compared to this worst model? Okay, and that's where we get the R squared from. Okay, cool. Any questions on that? That's a little subtle point that I think might not be the most clear, but I think it's an important one to distinguish, saying where this is coming from. Okay, no questions so far? Thumbs up so far? Understanding it sideways, like, okay, cool, good. All right, so most of this stuff is like calculation. You'll see, like, as you do you use stat models, for example, different libraries, you'll find out it's like, oh, you don't really need to know all the details, but it's important to know when it does work. And so a good thing is basically saying, when would a linear regression line work? So let me ask you guys first. For you guys, what do you think a linear regression line would not work well? Any ideas? Just throw them out there.
If your data is correlated exponentially.
Okay, good. So if your data is correlated exponentially, which I think what you're saying is like your data would kind of look more like an exponential curve, like your data kind of goes like this or something.
Yeah.
Okay, cool. All right. Any other times? When else wouldn't it work?
It's just not correlated at all.
Not correlated at all. Good. Just random noise. If your data, for example, looks very close to, like, I'm having a hard time drawing, but if it's like a big blob of nothing and it's basically equally likely for any point to be there, your linear regression is not going to do anything, right? Because it's random. Okay, cool. Any other ideas?
Just other non-linear regressions.
Okay, other nonlinear. So like Paul said, exponential. Jonathan said more like it's not correlated at all, which means like it's random. Other things could be like if your data looks like this, right? A linear regression is not going to do a good enough job to actually describe that, right? Your linear regression might actually look like this, you know, but of course that's not useful at all. So yeah, basically it's like if your data is not linear, essentially you can say, or linear regression is not going to work. What solutions might you try doing if the data isn't linear? Should you just throw out linear regression completely and say, not worth our time at all? Or do you think there might be ways to go around that?
I'm sure there are other formulas based around some kind of R squared thing, but using a different line, different shape line.
Okay, good. Yeah. So there are things using different shaped lines. So for example, if we had the one like Paul said with exponential, we can actually maybe have a model that is an exponential curve, right? And go through there. One thing is kind of the opposite way, which is really interesting, is that instead of making your model exponential, what you do instead is like you take the data and you try to make it into a linear function. So if your model, for example, is exponential like this, maybe you basically try to take the log of it and try to get it so it does end up being a linear function, and then you can fit a linear regression on this and see how well that fits. And then you can kind of essentially reverse your linear regression to get into a function, but you know it fits well because you did you did the R squared values with the linear regression. So that's something to kind of keep in the back of your mind that you could do. Okay, but let's kind of go into a little more detail because there's a couple other things that more for statistical testing. So first thing, like we said, if you have a linear part, probably can do that. Note that also linear can obviously be like in the negative direction. That seems pretty obvious. We have something very similar, like what Paul said, an exponential curve. It could be a parabolic curve and all that stuff. That's when we have to consider maybe not using linear regression or changing how we approach the model. Because remember, we could transform the data and try to fit a linear regression in there. It might not be the best choice though. Okay. The other part, which actually is not necessary to have it this way, it's actually a linear regression will work on non-normal, it's called on non-normal distributions. It will give you an answer. It can help explain things. It's not necessarily required that the data is normal. It's just that if we have it normal, we love normal curves because we can do statistical testing on there. So when we have this guy right here, again, not getting all tongue-tied. Basically, we can't do some stat testing, for example, z-test, it's a very common one that we try to go through because it's very simple and very quick for us to calculate. Confidence interval, for example, we kind of talked a little bit about p-value. This kind of like ties in with our p-value and saying how confident we are the regression line does match with that. We can't do that kind of analysis if we don't have a normal distribution. So one way we can do that basically is visuals. And so kind of a warning, we can do something called histograms, which we've already known before. We can see this histograms on the left and right. We can see skew, we can see data peaked. And this data peaked right here, kurtosis, that's kind of like what we're seeing. Skewed over this way. This is a nice normal distribution. There's also something called a Q-plot, which basically is just another way to show, it's a little more complicated. I actually think the curriculum does have an article. It doesn't go into full detail of how it's calculated, but basically it's testing out saying how far is it from a normal curve. So you can see your Q-plot, your data points right here, if each of these are data points, gets mapped onto basically a line right here, if it is a nice normal distribution. If we don't have a normal distribution, or at least something that's different from a normal distribution, we'll see that it deviates from that linear part right here. Like you can see this curve. And so one thing that you might ask is saying, well, okay, I see these plots here. I see like, these are not normal, but how do I know numerically if it's not normal? And there's a lot of debate on that because there isn't a clear, this is the one way you figure out if it's quote unquote normal, right? A lot of it ends up being, if you can plot it really quickly, you can quickly see, hey, is this normal or is it not? And then applying saying, well, if I want to quantify that, maybe put in a metric. But in reality, a lot of it comes down to subjectivity. There's not an objective way necessarily to say this is normal, which is why you as people, as data scientists, have to come in and say, can I apply these tests or not? And you have to decide, does it make sense for me to apply this test? Does it look normal? Essentially, is it close enough to normal that it won't make a difference? Or you say, you realize, for example, oh, this data would be normal if I exclude these parts of the data. And you have to decide, would that make sense? Is it okay to exclude these parts of the data for this context? So for example, if someone just, there were some outliers because of some, I don't know, there's a bunch of people who just randomly put in like inputs in a survey, and that made a huge difference and made it non-normal. Maybe it's very skewed, but you realize looking at the data, like, oh wait, those are definitely not supposed to be part of this population. So you can actually remove them. But again, it's context. A lot of times you can't do that. It all depends. Okay. Any questions on that so far? Okay, cool. And again, the curriculum goes into much more detail about how to calculate the part and how to run the code on it. Okay, the last one, this one always gets me. I can't say it. It's heteroscedasticity. I tried so far, like I was trying to do a pronunciation on like YouTube and Google. I'm like, I have such a hard time. But basically, the main idea here is we actually are looking to see if, again, if it's essentially nice and normal, but we're using the residuals. So the residuals, if you recall, I'm going to kind of scroll all the way up here again. Our residuals is basically how far our data was from the model, from our regression line. Basically what that difference is. So if our residuals are nice and spread right here, this homeoscedasticity, it's homeoscedastic, if I remember that right, that actually means that we have a nice model versus something where we have more of the residuals to be, what's it called? Like they're not evenly spread out. And so this is actually kind of a really subtle point that I think it's kind of hard to explain. And well, let me get back to it in a second. But here's a couple other examples, for example. This right here on the far left, this no problem, it says like no problem. Basically you have very good spacing of the residuals amongst the different points. But over here, you actually have something that's definitely like it gets less accurate. Or seriously, yeah, like your model's essentially getting less accurate as it goes on, which likely suggests that your regression line is not following, is not predicting the data well, and you have to do something else. Same thing here for a nonlinear part right here, is that maybe this might happen because there's a different kind of structure to the data that it's not linear. But this heterodacity is kind of a big one. That's kind of subtle. And I actually kind of have like a little story to it to kind of explain where this comes from. So back when I was doing physics, I remember my professor telling me like a story of a story, but like was telling me a story basically that back when he was doing graduate school, they had to be presenting papers and everything like that. And he was in particle physics, so they're doing a lot of this analysis. I mean, a lot of ways, a lot of particle physics ends up being like data science-like. And he was with his advisor, and they were sitting and watching basically one of his peers, like another grad student, present this paper. And he basically, he kind of described it that the way, because if you ever seen like a presentation of a scientific paper, usually they'll have the data points, and then they'll sometimes, like, you know, let's say they have the model of what it should look like, and then they'll also have like error bars. Do you guys know what error bars are, or have seen error bars before? Okay. So error bars usually is like a standard deviation of how likely that point like would have fallen in there. Well, he said the interesting thing when he presented his data, he actually found that there's the model, and the points obviously did not fall perfectly on the model, which is what you'd expect. But he found that the error bars all overlapped within that model. And that, you know, there's nothing that's specifically wrong with that. But the thing is that you would expect, like kind of like with the p-value, if you test it enough times, you would eventually have a point where the error is much further out. You essentially have an outlier. You'd expect outliers to happen just out of pure chance. And his advisor said, like, do you know this grad student? And he said, yeah, he's really, really smart. He's a really, like, he's really great. And his professor was like, hey, he was like, hey, what, like, is he hardworking? And he's like, yeah, he's super hardworking. And he's like, all right, I don't believe anything he's saying right now. And he said that because he could tell, like, you could take out certain data points, or maybe accidentally take out those data points and realize, oh, only these parts fit my model. That's the ones I'm going to use. So that's very related to this heterodicity. It's basically, you want to make sure your residuals do follow essentially, like, you don't want your data points, how do I say this? You don't expect every data point to be exactly on the model, and you don't expect it to have a certain, like, you don't expect it to have a relationship as you go through the data to have that difference change over time. If it does change over time, that means there's some other factor that you're not considering. And that's really what this is coming out to, saying, hey, do I have it, does the model, do the data points from the model vary in the way we expect it from random chance? So again, a little subtle point. There's a good, I'll make sure to send this out to everyone on Slack, but this explanation I thought was really good to talk about what heterodicity is and what homodicity is and why that's important. Okay, so that finishes up my guy for linear regression, really relationships on that. So any questions you guys have?